Alright, today we're going to talk about the second part of electrical circuits and components, and this is going to be the parallel circuits, okay? So as a quick reminder, earlier we talked about if I had series like this is R1 and R2, I calculated the total resistance as being R1 plus. I just merely added those two together, right? And that's how I do the series. When you're in parallel, okay, things are a little different. In parallel, let's say that I had a resistor here and a resistor here. So I had R1 and R2, okay? In parallel, the way you do this is the total resistance is like this, okay? So, let's say that I had, this was 2 ohms, and this was 3 ohms. So my total resistance would be 1 over T is equal to 1 over 2, 1 over 3. So this would be 6. If I do the common denominators, I get 5 over 6. So is going to be, if I flip both sides, I get 6 over 5, which is 1.2. So I started with 2 and 3, I ended up with a total resistance of 1.2. Okay, so this is how you would do the parallel circuit. Okay, so let's see if we can go ahead and use this and do example 12.5. So example 12.5, I have one 9-volt battery hooked up to 3 separate resistors. So I have a 9-volt battery hooked up to 3 resistors. Let's move this guy in the middle. That. So this is 9 volts. And I have R1 is equal to 3. So R1 is equal to 3 ohms. R2 is equal to 7 ohms. And R3 is equal to 9 ohms. Okay? So the voltage drop, so let's go ahead and calculate the total resistance. So total resistance is 1 over 3, 1 over 7, 1 over 9. As such, so you find the common denominator here would be 63. So 3 is going to be what? 21. 7 is going to be 9. And 9 is going to be 7. So I add these together, I get 16. So my total resistance is going to be, flip both of these sides over, my total resistance is going to be 63 over 37. Okay? So that's my total resistance. Okay? So what is it asking for? What do I need to do? It says, now determine the current flow through each branch. Okay? So this is my total resistance. So since this is my total resistance, and this is my volts, my amps are going to be what? My I is equal to V over a total, right? So I'm going to get what? I'm going to get 9 over 63 over 37, which is the same as 9 times 37 over 63. That's 7, so I get what? That's about 5.2, so that's about 5.3 amps. So 5.3 amps. So what's happening here? So the 5.3 amps is coming out through here. It's going to go to here. It's going to this node. And now it has actually 1, 2 or 3 branches. It can go 3 ways. Okay? So let's go ahead and calculate the amps for each of these, right? So the amps, the I1 is going to be equal to V over R1. What is the voltage drop across this? Well, the voltage drop across that is the same as this, which is 9, right? So you have 9 over 3, which is going to be 3 amps. So I have 3 amps coming down here. Let's go with this one first. So I get I3 is equal to voltage drop again. The voltage drop across here is the same voltage drop across here, right? Because there's nothing in this line. It's the same node, really, the same points, right? So I get 9 divided by 9, V divided by R, right? 1 amp. So I have 1 amp here. Over here I get what? I'm going to get R, so I2 is going to be equal to 9 divided by 7, which is 1.3 amps. Right? So what's happening? I have 5.3 amps that comes through here, of which out of the 5.3, 3 of them go down here, 1 go down this, 1 amps go this way, and 1.3. So if I add these 3 together, 3 plus 1 plus 1.3 is 5.3, right? And what is that? Where does that come from? The Kirchhoff's law has to be satisfied at this point, right? The Kirchhoff's law says what? The incoming current is the same as the outgoing. So I have 5.3 that comes in, it goes out 3, 1.3, and 1. Okay? All right. And also, you can calculate, if I asked you, you could calculate the power across each of these, right? The power would be what? Power is equal to, power is equal to VI, right? The V is 9, I is this, so this would be 27 watts. That's a watt. Over here, I'm going to have the power here is going to be equal to the voltage, which is 9 times that. So it's going to be 9 times that, so it's going to be 11.7 watts. Over here, the power is going to be equal to the voltage, which is again 9 times that, so it's 9 times 1, 9 watts. So you can calculate the power consumption across each resistor also. Okay. On page 415, it gives you a series and parallel together type of situation there. So let's look at that quickly. I'm not going to go through the entire thing, but I'll set it up for you. So this is 12.6. 12.6. On 12.6 you have again a 9-volt battery with a resistor here, and then I have 2 that are in parallel. Okay, so I have 9 volts here. R1 is 3 and then 7 and 9, so I have 3 ohms, 7 ohms, and 9 ohms. And what is the question? And they want us to determine the total current drawn by the circuit. So total current, so in order to find the total current, you have to find the total resistance. So what I'm going to do first is I'm going to put this guy as in 1. So I'm going to go ahead and change this, or put an equivalent circuit that looks like this. So this would be same 3. Now I have to find the total of these two and put it right here. So the total of these two would be what? 1 over RT is equal to 1 over 7 plus 1 over 9. 63, 9 plus 7, 16 over 63. I flip both sides, so RT is going to be equal to 16 over 63. So this guy here is going to be 63 over 16 ohms, right? So my total ohms, since now I have a series circuit, I can just add these two together, right? So I'm going to get, now the real over here is going to be what? I'm going to get 3 plus 63 over 16. 16, that would be 48 plus 63. 111 over over 16. So that would be my real total resistance on the bottom one here. And I have 9 volts here, so the current is going to be what? Current is going to be 9 volts divided by, this is the resistance, so it's be 111 over 9 times 16. Okay, you can go on from there. All right. Last but not least, there's this thing called capacitors. We're not going to deal with the capacitors. Capacitors is something you can do later on. Just know that it is a component that stores electrical energy. Okay, and it is measured in farads, so it's basically picofarads or microfarads. Okay, and we'll call it a day.